I'm John Wayne. You've seen me in such fine quality chemistry educational videos like electrochemistry and electroplating. What do they have in common? And galvanism, galvanism, my heart for galvanism. Okay, well this video is meant to be pretty short, just a very quick introduction to the idea of electrochemistry and what's exactly involved in a galvanic cell. How does that work? What's going on with that? So if we look at electrochemistry, we're looking at an interchange of electrical and chemical energy. Now they're both energy, but it is different. Because electrical energy, basically it's made up of electrons. Oh, call me crazy, electrical electrons. No connection whatsoever. Yeah, right. But the thing is that these two processes do involve the redox equations. Now, you might talk about oxidation and reduction, okay? But the idea is if you're generating electric current from a spontaneous chemical reaction, that'd be kind of important. Remember, spontaneous means that you don't have any outside interference. The reaction is just going to go, okay? Whereas if it's the opposite process, and this is where you get into electrolysis, which can be used for electroplating things, okay, you're using current to produce a chemical change. So you have to put some electrical energy into it. You have to put some oomph into it in order to make it happen. But of course, we have to do a quick review about oxidation reduction, okay? There's the bottom line about redox reactions is that they involve a transfer of electrons. That's really it, okay? Because without it, you're not going to get chemical reactions happening. You're not going to be getting an electricity going either. Electrons have to move. Who would ever thought that the smallest subatomic particle, okay, has so much influence? You'd be amazed. Okay, so quick ones here. Leo the lion goes grr, okay, lose electrons, oxidation, gain electrons, it's reduction. Or oil rig is another one. Oxidation is loss of electrons, reduction is gain. So that's another way to remember that. Now, here, just very quickly, the oxidizing agent, okay, takes electrons from another species, not an animal, another compound, another element, and thus result is reduced. So the oxidizing agent picks up electrons. That's really it. Whereas the reducing agent loses electrons. It's the opposite. It's oxidized, but it gives electrons to somebody else. We've got a little bit some oxidizing agent examples like oxygen and ozone and so on and so forth. Okay, that'd be kind of an important thing for oxygen because, oh, I don't know, cellular metabolism maybe? Yeah, stop and think about that for a moment because oxygen is kind of destructive in that regards, and it needs to be because how else are we going to do the cell respiration? Whoa, yeah. Reducing agents, we can look at things like ascorbic acids, and phosphites, and carbon monoxide and carbon. Okay, all those things are great reducing agent examples. Okay, applications, well keep in mind, moving electrons is the electric current. Okay, that would be a key thing, and we got a cute little reaction up there, but we kind of need to break it down. We've got MnO4 and iron running loose out there, and we can break it down into half reactions, which is part of the redox. Okay, because somebody, the bottom line is, somebody is going to lose electrons, somebody is going to pick up electrons. If they lose electrons, they're oxidized, they are a reducing agent. Okay? So what happens? So let's say we've got two beakers, we put in an anode and a cathode in there. All right, and we'll get to that in just a moment. Now, on one situation here, we have got iron in a solution, and here we have hydrogen and MnO4, manganese oxide, in another solution. And we can run it, the reaction starts, and it stops as soon as it goes through. Well, what happened? Well, you had a quick transfer of electrons, and what happened was you had all the electrons travel to this area, and that was it. You couldn't do anything else. It stopped almost immediately because the electrons are like, whee! And that's it. So something is not working. And this is where we have to deal with the idea of the basic galvanic cell. I'm not covering the entire chapter for those people that are wondering. Okay? But in the basic galvanic cell, you have an anode and a cathode. The anode, this is where the electrons are going to travel from the anode to the cathode. Okay? In there you have the reducing agent. Here you have your oxidizing agent. All right? Now there's two ways that we can handle this to make a very basic galvanic cell. One, we can put a porous disc here. Well, what is that going to do? It will allow anions to go through here. It will allow them to go through. Okay? And the same idea here with a salt bridge. So this is two ways you can solve the same problem. Because the problem that you're running in, when you look at this here, once you connect it, you now have developed a charge, and now it's stuck. It can't do anything else. One side is going to be positive, the other side is going to be negative. There's no interaction. There isn't. So there's got to be some give and take somewhere in order to make this cell happen. Because the cell's only going to work very, very quickly. And part of the problem when it works that way, we cannot take advantage of the chemical energy. And yeah, we're going to get some heat from this, but again, that's not going to work for a battery. That's a very important thing. So that's when we talk about the basic galvanic cell. That's why we put the salt bridge. That's why we put in the porous disc, so we can allow some kind of an exchange of ions to go through. Yeah, because what's up here, guys, is you got the positive, you got the negative. But once you connect this, then you have the net charge is zero. That's a very important concept here in electrochemistry for that. Very, very important. Because if the net charge isn't zero, you're not getting any of the battery action. That's not happening. Not in this world or the world to come. Okay, unless the laws of physics and chemistry have completely changed. I don't think that's going to happen. So, galvanic cell, again, a salt bridge does allow the current to flow. So, by doing that, now we can have a shifting. We can have electrons move forward. We have anions moving forward. Okay, and what you end up getting, ladies and gentlemen, is that the electricity travels in a complete circuit. That's what's going on, because now electrons are able to go through, and thus we are able to continue on with the process. Okay? The porous disc also allows ions to flow without a lot of the mixing of the solutions. Now that's a very important thing. You don't want the complete mixing of all the ions, because if you do that, we're not going to get any electrical action out of it. We're not. We're going to get squat. We're going to get nothing. Okay? We want to keep it where we only let in a little bit of it go through. Just enough to keep the cell going. That's the key. That's a huge, huge key. Okay? And then here, well, how does that work here? Well, again, here's your anode, and here's your electron going through, whee, and it's going through the wire, and it's going into the cathode, and then it's going back through oxidizing agent and our reducing agent. So there's kind of a circle that goes on here with that, and that kind of helps. Okay? As I look at this, there's a few things that would be useful to really know. One is what the cathode is. It's where the reduction happens. Remember, you're gaining electrons. That's what the cathode does. It picks up electrons, and we like to call that the red cat. That's a nice way of remembering that at the cathode, okay, you have the reduction. But in the anode, that's where you have the oxidation occurs. That's where you have an aux. So we have our red cat and we have our aux. That's a great way to remember this. Now remember about oxidation and reduction. Okay? Oxidizing agent, reducing agent, very, very useful to have. Okay, summing up our galvanic cell fairly quickly. Solutions need to be connected so that the ions can flow to keep the net charge zero in both compartments. Because if one side is all positive and the other side is negative, we're not getting anything. The second thing is the chemical energy is changed into electrical energy. Wait, how's that happening? Well, remember, compounds break up and you get electrons as part of it. The third thing is the salt bridge or the porous disc allows the ions to flow without too much mixing of the solutions. Because if the solutions mix too much, then the cell isn't going to work. Okay? The electrons flow through the wire from the reducing agent to the oxidizing agent. Okay? And with that, guys, I'm hoping that gave you a little bit of a clue on the galvanic cell. This is the basic principle how batteries operate. Okay, that's it. I hope everything works out well for you guys, and have a good one.